So, those of you that were in the session this morning would have heard how we went through verification methodology and a very quick overview of SystemVerilog. The idea of this afternoon's session is we're going to take a look at getting started with UVM. So, how would you put together your first ever UVM sort of Hello World program? So, we'll see the steps involved with doing that. Try to show you it's actually quite easy to do that, but it's quite a bit of code to write. And then for the second part, we'll compare and contrast that with how can you get started with formal verification. So what's involved there? How is formal verification different from UVM? Should you be using one rather than the other, or perhaps maybe both? Okay, so again, we've got quite a lot to cover. So as for this morning, I'm not expecting going to give you a detailed description of the code of every slide. But there is a link to a couple of EDA Playground that you can explore if you want to play with these things further with the UVM. Unfortunately, we haven't got formal verification tools yet on EDA Playground, but hopefully that's something that will change in the future. Okay, so hopefully this will work. We did earlier. No. Try again. Right, so this first part, we're going to be taking a look at UVM and having a quick look at how we can go through a very simple getting started with UVM. Now, I think I've recognised a couple of faces from last year, so you might have seen this last year, but try to sort of condense it a bit and say separate out the SystemVerilog part. So, what is UVM to start with? It's the universal verification methodology. It's an IEEE standard that was defined for SystemVerilog. And so you need to be using a SystemVerilog tool, one of the standard simulators like Excellium or VCS or QuestaSim or Riviera in order to do it, to run it. It's based on constrained random coverage-driven verification. So randomly generating the inputs using functional coverage in order to determine whether you've done enough simulation. It's not IEEE standard, but it's actually open source. So you can download the source code from the Accelera website. You can make any modifications that you want to if you want to make your own custom versions and so on. Okay, so it's under an Apache 2 license, so you're free to do that. And so the main thing is it's supported by all the vendors, and it is the most common verification methodology out there at the moment. Okay, so there it's been copied or emulated, should I say, by other languages. So there's a System C version of it, and you might have heard about things like the VHDL, OSVVM type of environment as well, which is trying to do the same sort of thing, but they're not as comprehensive as UVM. So UVM, you can think of as being best practice. So it was designed by verification engineers who knew what they were doing. They designed it to allow you to effectively copy the style that they were taking, so you can repeat it and don't have to reinvent things yourself. And reusability was a key requirement because it takes a lot of time to write all this code. So UVM gives you an off-the-shelf library of base classes that you can then inherit, modify, and that gives you all the main elements to put together your test bench without you having to write all the code yourself. Okay, and one other point, it's not only code, it's actually people and know-how. So don't underestimate the fact that if you can hire somebody who already knows UVM, then they can get straight to work. UVM itself has been through several revisions. So the original version came out back in 2011, and one of the most currently used versions at the moment is this UVM 1.2 that's been around for almost 10 years now. It is an IEEE standard. We're slowly starting to see people adapting or adopting the IEEE standard, but it's not by no means universal at the moment. There are some minor differences in the IEEE standard, but they don't affect what we're going to be looking at today. So there's various versions of the code you can download, and you can even download the language reference manual free from the IEEE as well, if you want to know more. So there's a couple of links at the bottom to give you further information. So as I said, it's based around constrained random verification. Hopefully everybody knows what I mean by that, but just in case, here's a quick slide. We've got our design under test. If we've got random inputs, they're constrained to make them useful, but for that to work, we need to have some kind of automated checking because we're going to get random outputs and we don't know what those are going to be. We need functional coverage in order to check to see what our random inputs has really been doing. So has it tested everything we need? And if it's not, then we probably need to look at the constraints. So modify the constraints in order to fill in the missing gaps in our coverage. Okay, so that's the basic idea. Now, in terms of a typical UVM test bench, the architecture will look something like this. Okay, so what we have is we've got a UVM environment. So everything is sitting inside this environment. So that UVM env would be a base class or component derived from base class in UVM. Inside our environment, we've got different types of component. So we've got components with names like UVM agent, subscribers, virtual sequencers. So those are basic building blocks. We're going to focus on what goes inside this UVM agent, because UVM agents are designed to be reusable verification components. So typically, each agent will be associated with a certain type of interface. So you may have an AXI bus interface or an I2C interface and so on. And each one would have a corresponding agent that understands the protocol. The reason for that is that inside our agent, we've got a driver and a monitor. And the job of the driver is to drive this interface with whatever protocol. But the input from the driver comes from a sequencer, which generates transactions. So we've got a transaction level operation inside UVM, which is great for efficiency. It's also great for reusability because the transactions abstract away the low-level protocol details. So if we want to generate a stream of values for a particular functionality, then we're not locked into a particular protocol. So the driver does a translation going to the DUT. The monitor does an inverse translation to generate transactions back from pin wiggles on the bus. We've got the interface is connected to our device under test, and we've got one or more UVM tests which are going to basically configure the environment and set it running. For configuration, there's a couple of mechanisms we can look at. There's a factory. So that uses the object-oriented factory design pattern to determine what types of components and sequences we're going to run, and a configuration database, which is good for setting up the initial conditions. Now, when you run a UVM simulation, then the UVM environment is created during initialization. So in the initial phase, when you start your SystemVerilog simulation, that's when UVM gets created, or UVM environment gets created. So everything has to happen after that. And with lots of components, there needs to be some kind of ordering. So we want, for example, everything to get built before we try connecting things together in UVM. We don't want to start running any kind of equivalence of processes in our classes before everything's connected and so on. So the UVM provides phases to manage all of that. So initially there is a build phase. So during the build phase, that's where UVM components get instantiated. Okay, so here's our environment. It's going to be running top down. So the environment instantiates a subscriber and an agent. The agent in turn is going to instantiate its sequencer, driver, and monitor components. Okay, so that's the first phase. Then there's a connect phase. The connect phase is going to make the connections between these components. So these are all transaction level connections. There's then an end of elaboration phase. This is like a callback function which can be used for whatever you like at that point. So you may want to do some checking to make sure things are connected up. Maybe you want to pick up some names in the hierarchy to set up probes in your test bench and those sorts of things. Starter simulation is typically used for doing things like opening files that you may want to read and write to. And then it goes on to a run phase. Now, the run phase is the only part of UVM that consumes time. Okay, so these other ones just functions. The run phase is a task, and in that run phase, then sequences are run on sequencers. A sequence is just consists of a task which generates a stream of sequence items. Each sequence item gets sent to a driver, which then breaks it down into the pin wiggles to drive the device under test and so on. Now, sometimes it's useful to be able to break up what's happening in the run phase, because the run phase is going to happen simultaneously for all of the UVM components. But you may want to have some components where perhaps you want to have a reset and you don't want other components to start generating sequences until everything's been reset. So you can break down the run into these other simpler elements. There's a reset phase, a configure phase, a main phase, and a shutdown phase. And then there's also these other pre and post versions of those if you want to have even more fine granularity. Typically, these are used for running particular sequences. So you may have a sequence that runs in the reset phase and a different sequence that runs in the main phase. So that's where those will be used. They're not normally used in components like monitors and subscribers, where the behavior is always going to be the same. Then when the run phase finishes, that's the end of the simulation. But before it exits, there's an extract phase, check phase, and report phase. And then finally, a final phase, which is the last thing that happens before it shuts down. Okay, so these are all functions apart from the run phase, which is the task. And you can override these for any of the UVM components. So the way that you proceed is typically you would create some component by overriding one of these UVM base classes and then specify these overridden functions or tasks to do what we want to do at that point. Okay. So you can focus on the special features of each component and all of the behind the scenes things like making things run and talk to each other and so on is managed by the UVM internally. Okay, now I mentioned the factory. The factory is using or based on a common object-oriented design principle or design pattern. And the idea behind it is it allows you to customize what type of components get created. So inside your code, you'll have, for example, a sequence, and that's going to use a sequence that's going to run on a sequencer. And you might run your sort of initial version where the sequence will use a particular type, and then you might want to modify that to use a different type for a particular test. So that's where the factory comes in. So the factory applies to components, sequences, and even transactions. And so what you could do is you could write some code for your initial test, and maybe your sequence uses type T1, but then you want to run a slightly different test where it's still going to use the same protocol, but you want to create perhaps a different pattern, different constraints. So we can create a new class T2, and then we can program in a factory override. So what happens next is that when you run your UVM simulation, rather than creating objects of type T1, objects of type T2 are created for that sequence. So it gives you a way of being able to effectively program what your UVM environment is going to do without making any changes to the source code in that UVM environment. Okay, so that's reusability. Okay, so let's have a look at how we can get started with UVM, and that will highlight some of these points. And we can take an absolute minimum example that's just going to print hello world on the screen. Okay, so it's not going to be a useful test bench, but it will show us how the bits relate to each other. So what we've got is we've got our environment and we've got a test. So we need those as a minimum, okay, because we have to start a test and the test is going to create the environment. But we don't need to worry about things like agents initially. Okay, so that's what we've got. And our core features are we've got a module that's going to be our device under test. Again, that's going to be empty initially. We've got an interface that's going to be used for making connections, but we're going to leave that empty for the time being as well. And we've got a top-level module that creates an instance of our design and test, and an instance of the interface, and is also going to have to start our test. Okay, now what do we need then as a minimum? Well, we need an environment class. The environment class in this case is going to be really simple. So the environment inherits one of these base classes. So UVM env is the base class for environments. We're creating our own custom version of that. When we create our custom environment, then we're going to use it with the factory. So we have to use this macro. So UVM component utils is a built-in macro with UVM. And what it's doing is it's basically telling the factory about my env. Okay, so having done that, we can then use the factory to create an instance of my env. The other thing we have to have is a constructor. Now, my UVM env is based on the UVM component type of object or class. So the constructor for UVM components takes 2 arguments. So every component has a name and it has a parent. So we can keep track of a hierarchy. So if you compare this to what you have in Verilog or SystemVerilog, where you've got a hierarchy of modules, then you can use SystemVerilog hierarchical path names to pick up low-level components. If you want to, for example, probe a wire in some subcomponent, you just give it a hierarchical path. Well, this gives us the same ability for UVM classes. So when we create instances of components, we want to be able to pick up things that are present in lower level components. So we have to pass in the name and the reference to the parent, and then we just call super.new. So that's calling the base class constructor for UVM env with the name and the parent. Okay, so that's our environment, but where's our hello world? Well, the environment itself is created by the test. Okay, so to create a test, we extend the UVM test base class. Again, we need our UVM component utils macro and our standard component constructor. We're going to create an instance of the environment. So here we have a variable for that, and we create a hierarchy in the build phase. So to override the build phase, we've got this function build phase that takes a single element UVM phase, and then we've got one line in here which is going to create that environment. Now, if you're familiar with SystemVerilog or you're present in this morning session, I said that to create a new object, we just call new. Well, that's fine if we're not using the factory. So UVM provides this create function instead. And the idea is that the create function is going to call new, but before calling new, it first looks up to find out what type of object it should be calling new. So that's how we've got this customization. So if we've overridden the factory, even though we're calling here create for my_env, if my_env has been replaced with a different type of factory, we'll get that different type. The only requirement is it has to be a type that is derived from my_env. Okay, so that's our hierarchy. And then grayed out here, we've got a run phase. So let's have a look at that. So the run phase happens at runtime. So this is where our behavior is going to be executing. And it's a task rather than a function. Okay, so all the other ones were functions. Now, the way the run phase works in UVM is it starts at time 0 and it will run for as long as there's some work to do. Now, if you've got lots of different components, they each have their own run phase. So how does the simulation know when to stop? Well, UVM has a mechanism that's known as objections. And every run phase, if you want to continue, there must be an objection for the run phase that has been raised. So to make sure the simulation doesn't stop immediately, first thing we're doing in here is raising an objection. So that raises an objection for the run phase, so the run phase can't finish until that objection has been dropped. So that affects all of the other components that are also have a run phase. So if you don't do that, the simulation would stop at time 0. So sometime later, after time 10, here's our hello world. We're just printing out a message. And UVM has a report handler which uses macros like this UVM info to print out messages in a controllable and consistent fashion. So when we run it, we'll see our hello world message. So there's nothing else we want to do in our hello world program. So we then drop the objection. When the objection's been dropped, no other components have got a run phase that raises an objection, so the UVM will exit. Okay, so that's all we need to do in our simulation. Now the test itself has to be created. And just before we do that, just to summarize how we're writing our code. So we've got a file here that contains all of our code. So we're including one of the UVM header files, which gives us the macros we've seen. And we've created a package to put all the rest of our code in. In that package, we're also importing the standard UVM package, which then makes all the UVM features visible. And then we're putting our classes in there. Okay, so this is ideal for reusability because we just got a package. We can use that or reuse that in any other test benches. If we don't need any of those classes, it doesn't matter because when you import a package, it only pulls in the items that you actually use. Okay, so going back to our modules, so we've got our DUT, the interface, and in our top level module, we're now importing the UVM package and the package we just created. And then as well as the device under test and the interface, we've added an initial block. So this initial block is what's going to create the UVM environment. So when we call run test, that run test will create an instance of my test. The instance of my test will then have a build phase that creates the environment, and then the run phase will print hello world. Okay, so that's basically the simplest UVM program we could come up with. Okay, so it's got the bare minimum. It doesn't do anything useful, but apart from print a message. So just to summarize how simple it is, this slide just shows all of the code we've just gone through. So there's not much code there. And so we've got the run test that pulls in the my test. We're pulling in the package, here my package, and we've got the links there between the different components. Okay, so how do we run it? Well, we can run it on EJ Playground. And you could log on to EJ Playground, it's free to use. You could create your own project or your own playground and type in the code if you wanted to. Alternatively, there's an example that's already written for you can try out. So if you were to type in this URL, then that will actually pull up a working example with this source code in it. Okay, so we can then run it. So in this case, looks like we've run it with Excellium. And what we see is that as it runs, we get this message coming up from the top level of the test, hello world. Okay, so we've done what we set out to do. We've got UVM running. So it's not doing anything useful yet, but at least now we can start trying to make something useful happen. Okay, now let's take a closer look at the interface. We'll see how we can add that. So the interface is there to connect the pins on the device under test to UVM. And the reason we need to have that interface is that we want to have something that we can easily use to access this sort of part of the hierarchy in SystemVerilog from inside a SystemVerilog class. So we don't want to store a hierarchical reference because that would break the rules about what we can put into a package. So an interface is useful because we can then use a virtual interface which we can access inside a class. And remember, a virtual interface behaves like a pointer to an interface. So it's just a number. So in our UVM environment, we're going to connect from our UVM environment to this interface. Okay, so we'll see how to do that in a minute. So before we do that, let's have a look at what we put into our interface. So in our interface, we've got some low-level signals, so clock and reset, command, address, and data. And those could then be connected up to the pins on the device under test. Okay, so inside our device under test now, we're going to change where we print our message. So now we're printing a message in the device under test, which is going to print out the values of those pins. And it's going to do that every time there's a positive clock. Okay, so that's what we're doing. So the actual clock generator and so on will be part of the either a top-level module or a separate test harness. Okay, so again, very simple here. That's what we've got. So how do we make that connection? So we've got our interface, we've got our environment, Then in the driver, so the driver, rather than adding into an agent, we can add the driver directly into the environment, keep things simple. That driver will have a virtual interface that holds the location of the actual interface. Okay, so that's what we need to set up. Okay, so that's actually quite easy to achieve. Now, we need to have some way of getting the virtual interface details into that UVM class. And the easiest way of doing that is to make use of the configuration database. And the configuration database is just a series of name value pairs, and each name value pair has a corresponding scope. And in the configuration database, the scope matches a hierarchical path name in UVM. So the names that we could give to the UVM components when we create a hierarchy can be used to identify which components a particular name value pair is going to be used in. So that's the idea. So we can set the contents of the configuration database inside this top level module. So here we can put in the location of this actual interface as a virtual interface, because that's visible inside the top level module. And then in the driver, we can call a corresponding get function, which is going to retrieve the value from the configuration database. So now we've got the virtual interface inside the driver. So we need those two steps. Now, in terms of the code for doing that, again, it's very straightforward, but it's something that people often make mistakes with. So I'll just go through here. So in our top level module, here's our interface called .if1. In the initial block, before we call run test, we're going to call set with the configuration database. Okay, so the configuration database, when we write something to it, we need to specify what type of object we're writing into it. So here we're writing a virtual interface, so we need to specify the type with the parameter as being virtual.if. And then the arguments to set are going to specify, first of all, a path name. The path name is built up of these first two arguments. First one is a starting location, so a parent component. Well, this code is running inside the top module, so there is no UVM component parent. So when we call set inside a module, the first argument is always null. And then the second argument would be the rest of the UVM path name. Now, this is very powerful because we can actually use wildcards here. So if we put a star there, that's fine for a simple example, because that means that this name value pair can be picked up from anywhere inside our UVM environment. Now, for a real test bench, that would be a really bad idea, because we may have lots of interfaces with names that just happen to be the same, and we don't want to have clashes. So normally you'd provide a path name that is fairly general, so that you can apply it even if you don't know exactly where the particular driver is going to be, but specific enough so that you don't get it appearing in the wrong place. Okay, and then the arguments here are just a name that we used to look up, and the .if, which is the same as the name of the interface. Okay, so that puts it into the configuration database. Inside the driver, we'll get it to set the virtual interface. So for the driver, we've got a class myDriver, which is now extending UVM driver. So UVM driver is another pre-existing UVM-based class. When we inherit that, then we get some functionality that's unique to the driver. In particular, we get a port which is connected to a sequencer. We still need to do the same steps as we saw previously with the components. So we need our UVM component utils macro with the name of the class, and we need our standard component constructor with a name and a parent. We've also added a virtual interface. And now when you're writing code like this, the virtual keyword here is critical, because a virtual interface is like a pointer to an interface. We can store that in a class. If I'd missed off the virtual keyword, then we'd be trying to actually instantiate an actual interface inside our class, and you're not allowed to do that. Okay, because that'd be like trying to put a module inside a class, which again would be disallowed. Okay, so now in the build phase for our driver, we're going to fetch the virtual interface from the configuration database. So we've got a corresponding call to the configuration database with the same type, virtual.if. We're calling get, and the first argument here, that's going to get mapped onto the hierarchical path name of the current component. So in SystemVerilog, it's a bit like similarly to C++, this refers to the current object for a class. So that will be the current instance of my driver. So if that matches the hierarchical path name that the top level module set up, then we'll pick up the matching name. So the second argument is normally just an empty string. That would allow you to add extra fields into the path name, but that's not normally used. And then we got the name of the variable we're looking for, .if, and its value. So it's important this string here for the name must be exactly the same as the one used when you called set. Okay, and then .vi, that's the name of the virtual interface that we want to set or to update in there. Okay, so we've now got the virtual interface. What are we going to do with it? Well, we need to wiggle some pins. So in our driver, we're going to add a run phase. So again, this is going to start at time 0, and the run phase is going to be in a forever loop. So that's fairly typical. We've got a at pos edge clock. So every time there's a clock on the interface, we're going to generate some random numbers and write those to the pins. Okay, so we use the interface, virtual interfaces, just like we would use a physical interface, and use the dot to access the members. Okay, so that's our driver complete. Okay, so we could then run our simulation, and what we'd then see is we'd get these random values being printed out by the device under test. Okay, so haven't shown the results for that, but again, if you look on EDA Playground, there's a matching playground for that as well. Now, to make a more sensible or realistic test bench, what we need is some way of controlling the stimulus, not just generating random numbers. So for that, we're going to create a sequence. Now, a sequence is basically just a stream of transactions. So here's a transaction. We're creating my transaction and inheriting the UVM sequence item base class. Now, we may want to change the type of transaction that sequence is producing. So we want to register it with a factory. So that's what we're doing down here. So in my transaction, we've just got a couple of random fields. So 3 random fields, command, address, and data. So that's what's going to the DUT. We've got a constructor. Now, the constructor for sequence items is simpler than for components, because sequence items don't form part of the UVM component hierarchy. So they don't have a parent, they just have an optional name. We still have to call super.new with that name. Now, to register my transaction with the factory, we're using a UVM object utils macro rather than UVM component utils. And that's because the constructor is different. So the constructor for a component takes 2 arguments. The constructor for objects only takes 1 argument. So when we get this gets registered, then the create function needs to call a different new. Now, UVM object utils begin allows us to follow that with what's known as field macros, and the field macros is going to basically generate some code automatically that applies to these 3 command, address, and data fields. So it's going to add functions for doing things like printing, copying, comparing those fields for transactions. And so that happens automatically. This mechanism here is optional, so you can do it for convenience when you get started, but for more advanced test benches, typically you wouldn't bother with those macros. You'd write your own versions of those functions. Now, to create random stimulus, we need a sequence. So we've got a sequence item, but we need a sequence that's going to generate multiple sequence items. So for that, we've got my sequence, which extends UVM sequence, and we need to specify the parameter, what type of sequence item is going to generate. Again, we're registering with the factory. We've got a object constructor with one argument, and then in the sequence we have a body task. So the body task is what's going to generate the stream of sequence items. And in this case, it's very simple. We've just got a repeat, and we're calling this UVM do macro. The UVM do macro is going to generate an instance of my transaction. It's going to give the user handle rec to represent that. It's also going to randomize rec, and it's then going to send it to the driver. Okay, so creating sequences is quite straightforward if we use these macros. Okay, so we've got a sequence. How is that sequence actually going to get connected to the driver? So what we have to run the sequence, we need a sequencer. Okay, so the sequencer is a UVM component, and there's a UVM sequencer base class, and in this case that's sufficient to use. We don't need to create a custom class here. We're just going to create an instance of UVM sequencer that works with my transactions. Okay, so we can use that off the shelf. And sequencers are components that run sequences. Don't mix sequences and sequencers up. It's a common mistake when people are learning. So a sequence is a component, is a stream of sequence items. A sequencer is a UVM component. Okay, and we're going to connect the sequencer to the driver. Okay, so we need to create this connection. That's using, let's say, a TLM connection. So we need to create our environment with a sequencer and a driver, connect the two together, and then we also need to make sure that sequencer is going to run that sequence. Okay, so in the driver, in order to pick up the sequence items, we've got this seek item port get. So the seek item port is a port, the TLM port that's inherited from the UVM driver. Now, this time we've modified the driver so that we've also specified the type of sequence item, because we need to make sure that the TLM port is the right type. That wasn't an issue for the previous example because we weren't connecting it to anything. So when we call get, that's going to fetch the next sequence item from the sequence. If there's no more sequence items available, then get will just stop. We'll just wait forever. Having fetched the sequence item, we're then going to wait for a clock and then send it to the device under test. Okay, so that's what we're doing there. Okay, now in the environment, it's a bit more complex because we've got multiple components to connect now. We've got an instance of the sequencer. We've got an instance of the driver. Okay, so both of those we'll need to call new create for. So in the build phase, we've now got two calls to create. One for the sequencer, one for the driver. Again, it's using the factory. And notice that when we call create, we specify this hierarchical name. Now, as well as creating those components, we need to connect them. So we've overridden the connect phase function in the environment. And in this case, we've got one statement. So on the driver, we've got this seek item port. The items in red, in case you're wondering, are the predefined names. Okay, so things that are already present in the UVM base classes. So the connect function then is going to connect the port on the driver to a corresponding export on the sequencer. Okay, now TLM connections use what's known as ports and exports rather than just connecting two ports together. But we don't have time to go into the details of that here. Okay, so in our test, we've got a bit more to do now, because in the run phase, we need to create that sequence. So we've created the sequence. The environment has a sequencer and a driver, but we still need to create a sequencer object for that sequencer, for the sequencer to run. So here we're creating the sequence object, and then randomizing it, and then before we start it running, we're going to use an alternative way of raising and dropping objections. So if we're running a sequence, then from UVM 1.2 onwards, the sequence itself can can raise the objection when it starts and drop the objection when it finishes. So we don't have to do it ourselves. So that's what this set starting phase and set automatic phase objection do. So set starting phase tells the sequence what phase it's actually starting in. So in this case, phase here corresponds to run phase, but it could be a reset phase or a main phase if we're using the other ones. And then set automatic phase objection with 1 means that when the sequence starts, it raises the objection to the run phase. When the sequence finishes, it drops the objection to the run. So the last thing to do then is just call start. When we call start, we're calling start for the specified sequence object. And we also need to specify which sequencer that sequence is going to run on. Okay, and then that's it. We've now got everything what we need to run the simulation. Okay, so when we run it, you'll run now in practice, we'll probably make it a bit more complex, and we'll probably put the sequencer and the driver into an agent together with monitors, but the principles are exactly the same. Okay, so that sort of, if you like, is UVM in a nutshell. Now, you might have noticed quite a lot of the code was similar between slides. So it's just basically boilerplate code. So that's one issue with UVM. Another issue with UVM is if you look at it, there's an awful lot there. So those of you who've got a UVM Jordan reference code will see it's quite thick. Okay, there's lots of stuff to learn. So to help, a few years back, we created our Easy UVM project, which you can access on the GEOS website. There's a link here. Firstly, it contains a whole set of coding guidelines to help you get started. So how do you create your UVM environment, naming conventions, which bits do you use, which bits do you ignore, and so on. And there's also an automatic code generator, which will actually, you enter some fairly simple templates, and it will actually create the UVM environment for you. Okay, so, and it will actually also allow you to make changes and to keep those changes when you rebuild, when you regenerate it. Okay, so it's about 5,000 lines of Perl if you're interested. Okay, so I do still maintain it, but not that often these days. It's because I've got too many other things to do. But if you do use it and come across a problem, then please do use our help desk to let me know. We found it been very useful to help people learn UVM because you can effectively generate a whole new UVM test bench without having to write all the code yourself. So that's great for exploring. It's also been used on real projects, and on an early project when it was still in its infancy and not very complete, the company used it on a project and they reckon it saved them about 6 weeks of development time. And they just ran it once to generate the initial UVM test bench, and then everything else they hand edited. But it was still very useful. And it also means that you can ensure that you've got consistency. Okay, so that's UVM. What about formal? So in the remaining time, let's have a quick look at how formal works. So we've heard quite a few presentations on formal today, but no one's actually said what is formal, how does it work? Okay, and that's perhaps the hardest question. Okay, so we're going to have a look at some simple examples to show that formal doesn't have to be something that's hard, and then we'll have a look at what's going on. So formal is very good for property checking. We can use that for bug hunting. We can also make sure that we're happy that our logic really is working correctly. So if you've got something like a safety critical design, you need to be very certain that that's not going to do something dangerous. So we can write properties, and then we can prove that those properties really are applying. So you can get certainty that's not possible with just simulation. We can even do things like built-in checks. So formal tools include some built-in checks, which are really just like glorified linting tools. They can find obvious bugs or coding errors that people are regularly occurring. It's a good idea to use formal from the point of view of getting you to understand the spec, because if you have to write the properties, you have to suddenly start thinking about the specification in a much more formalized way. So does it make sense? Are there any inconsistencies or anomalies? And they will become pretty clear when you start trying to write a property to do that. And you can even use it right the way through to actually debugging post-silicon. So as I said, formal is not hard to use, despite what you might have heard. So basically, you just give it your RTL code, write some properties. Okay, how do we write some properties? So here's our very simple RTL code. So we've got a module with a cell A and cell B inputs. So we're going to select either QA or QB and write it to the output Q. Okay, so here's our RTL code. If it's cell A, Q is QA. If it's cell B, Q is QB. Okay, and that will synthesize. It may be exactly what we want. Okay, so there's a priority in there, but if that's what you intend, then that's not a problem. So writing some properties. So we've got first property, a set of properties that cell A implies that on the next clock cycle, Q is going to be equal to the previous value of QA. So that's what $parse does. And similarly, we've got second property. If cell B is true, then on the next clock cycle, the value of Q should match the value of QB on the previous clock cycle. Okay, so that's pretty straightforward, not difficult. So to run it then, we've got our properties. We can press the go button and see what happens. So what might happen? Well, if we're lucky, we'll get a message saying that all of our properties are proven. Okay, so our design's working exactly as it should. If it doesn't work as it should, if it finds that there's a problem, we'll get a counterexample. So the counterexample will help you debug what the problem is. So why has your property failed? However, sometimes it might be inconclusive. So if you've got a design that has a particularly deep state path, so maybe it takes sort of hundreds of clock cycles between an input and then something happening, formal tools can't cope with that. They basically run out of memory. So it might run for as long as it can. Maybe you've set a depth of 20. It basically works through 20 clock cycles. It hasn't found anything that breaks the property, so it hasn't failed, but it hasn't conclusively tested everything. So therefore, it's inconclusive. Okay, so that will require further work. So if we ran formal on the previous example, here's what the results would look like. Okay, so we've got two assertions. So what happens? So two assertions, none of them are unreachable, and we've got two covered, which is good. Okay, so both of our properties, they could determine whether they were going to pass or fail. One of them's passed, but one of them has failed, because we've got this counterexample. So we need to explore and find out what's caused that to fail. Now, hopefully, if you're looking at the code, it's fairly obvious what the problem is. But to help you, the tools will generate, in the counterexample, a waveform. Okay, so we can see why has that failed? Well, it's failed when we've got cell A and cell B are both 1, and QA and QB are different. Okay, so if you look back at the source code, that makes sense. Okay, so we've got our counterexample. We need to decide what to do next. Now, this is where it can get hard. Okay, so it's easy to use, but we need to understand why the property has failed. Okay, so we've got assertions that have failed. Now, the assertions themselves, we can put them into our RTL code like we just saw. We may also have assertions on the outputs to check that our protocols are working properly. We may have properties which are actually testing the complete functionality. Now, end-to-end checks are typically quite hard to write, so that may not be a good place to start, but they can be very, very powerful if you get the results you want. Now, we can also put properties on the inputs as assumptions. So if we use the assume statement, then that basically limits illegal conditions from getting fed in, being considered as inputs. And that's what we would need to do in this example to get it to work. Okay, so we need to understand what formal. Now, to understand formal, let's look at the states. So if we've got a fairly small design here, I think it's about 270 flip-flops, then each flip-flop can be in a 1 or a 0 state. Okay. So what does that mean? Well, if each one of these can independently be in a 1 or 0, then the total number of states with n flip-flops, there's going to be 2 to the power of n. Okay, so with a relatively small number here, this becomes a very big number. Okay, so with 276 flip-flops, 2 to the power 76, 276 is actually about 10 to the power of 83. And to put that into perspective, that's roughly the same number of atoms are estimated to be in the universe. Okay, so it's not realistic to test every one of these states. Okay, so what happens when we run our verification? Well, if we're using simulation, then we normally start off by resetting it, so we know what state it's in. After the reset, there's a limited number of states you can go to next, and there'll be a limited number of states after that, and so on. So with our simulation, we basically scroll a path through the possible states. Okay, so we've got one path that we know should work. We'll do that again with other tests. And what we've ended up then with is basically a series of golden threads stepping through a particular set of states. But all of the rest is untested. Okay, so we can say, yes, we get to here, our design is working as it should do. But what about all these other cases that we haven't considered? So that's the problem with simulation. Okay, so what about formal? Well, with formal, it treats the state base slightly differently. So our target state might be, for example, we want interest in a particular output, maybe as a result of a certain number of preceding inputs. Okay, so the formal tool will look to see how can we get to that state. So it basically works back across clock cycles. Okay, so an example here, we've got simple property, request implies grant. So for that to work, the formal tool will try to find a sequence of states that would first of all make this fire. So request has to be 1, and then we can check to see whether grant is 0. So the formal tool will look to see all the preceding states to see which sequences of states would result in that request. And then are any of those going to result in grant not being 0? Okay, so we get what's known as this cone of influence, where it's basically stepping back through preceding states to find which combinations would actually result in our target state. Okay, and if any of those give us a situation where request is 1 and grant is not a 0, that's our counterexample. But if we don't find any counterexample, then it means that the property is proven. Okay, and the advantage of doing this is that we're not just testing one path through here out of many, we're testing a whole block. Okay, so if we can have sufficient properties, and each of those would be testing sort of a subset of the states, then what we're aiming for is to ultimately cover the whole state space. Now, for simple designs like state machines, that's not a problem, but for designs that have a huge number of states, like a memory, for example, or complex arithmetic circuits, then that's not going to happen. Okay, so that's the basic idea behind model checking. Now, let's go back to our simple example and find out how we can improve it. So here's, again, some results from the formal tools, actually highlighting values on the code. Okay, so I can't remember which tool it's from. I think it's from Synopsys formal verifier. But what we can see is it's highlighted under the cell A, for example, value of 1, Q is 0, dollar past QA is 1, and so on. So you can use that information to work out why is it failing. And hopefully you can see that because we're in our code, we're specifying that we're not specifying what happens if cell A and cell B are both 1. Now maybe that's going to be the condition. Maybe cell A and cell B can never be 1. So by working backwards from the information, we can then come up with a solution. Okay, so it's under constrained because we haven't written any constraints that limit that. Okay, so if cell A and cell B should never be 1 at the same time, we can effectively eliminate those from our truth table. So we need a way of specifying or telling the formal tool that that is the case. So this is known as under constraining, and we've got false negatives because we've got a failure where we shouldn't have one. So the solution is to write an assume property. So same syntax as assert property, with assume, then this will be limiting or constraining the inputs. Okay, so we're saying here that cell A and cell B should never be 1 at the same time. If we now rerun the form verification, we now see that we've got our 2 assertions are now proven. Okay, so it's a simple solution once we knew what the problem was. Now, you need to be careful with assume statements because you could also over-constrain the inputs. So let's say we got this wrong and we actually wrote the assume as cell A does not equal to cell B. Okay, well, that's actually eliminating values that should be considered. So that's going to give us false positives because we're not going to be testing things that we should be. So it says it's okay, but there may be a bug still. Okay, so that's a problem. How do we guard against that? Well, we've got to assume what we could do is we could make sure that we don't we don't have invalid assumptions. We could have a coverage. So we can have cover property as well. And cover property will check to see whether values are reachable. Okay, so let's say we want to have, for example, not cell A and not cell B is a valid input. Okay, because that should be fine. We don't have to do nothing. So we've added that as a cover property. If we now run that, what we find is that's now unreachable. So that tells us that we've got a problem with our assume. Okay, so here, our cover, one of them is unreachable. Okay, so we can then look at that and hopefully fix it. We could also run a simulation, because if we run a simulation, then the assume is treated in the same way as assert. So again, that would then give a simulation error. Okay, so if we fix that, what we then find is it's all now going to hopefully work properly. So if things do go wrong, we've got this counterexample that we need to debug. Okay, so things that can cause problems, we get false negatives resulting in the counter expression. That could be due to unconstrained inputs. Overconstrained inputs give us false positives. Similarly, we can get false positives if we don't have enough assertions. So maybe we haven't written all the properties, so we're not covering all those points in the state space that we need to. If you've got assertions which are perhaps not testing what they should be, maybe they're perhaps too broad, then that can be a lot harder to debug. Okay, so finally then, using formal. When to use it? Well, ideally it works at block level, and you can use that before you even run a simulation. So if you've got access to both tools, you could quickly run it through formal. That will pick up any obvious problems, and then you can focus on simulation. Okay, so they force you to think more about the spec, so that's good. Again, even if you haven't, because if you haven't written a verification plan, then you're going to have to do that when it comes to this as well. With the properties, they can stay in the RTL, and we can have different types of assertion ranging from simple ones through to more complex ones. Simple assertions are recommended because they're easy to understand and debug. Okay, bear in mind that formal and simulation have different strengths and weaknesses. So you may find some bugs in formal which are not detected by simulation and vice versa. So it's a different mindset, but it's worthwhile sort of thinking of things from 2 different approaches. So UVM or formal, our final question. So UVM is simulation based, so absolutely go for that. If you've got complex designs, then it's the established way of working. But don't overlook formal, because there's some things that UVM isn't so good at. And formal is particularly good at issues that things like control systems and so on. It complements simulation. So I would include both in your verification plans if you can. And we're increasingly seeing more and more people adding formal to their verification environments. Now, unfortunately, it's different tools. Those tools require licenses. So again, there are costs associated with that, which again is the sort of thing that puts maybe people often going down that path, but don't rule it out. Okay, and that's it. So thank you for your attention. I think I've just managed to get it all in the hour this time.